Hi there, Terry Brown, Mechanical Engineering here with another engineering mechanics video. So this will be just a lecture PowerPoint style video. So let's have a look at the PowerPoint. Okay, so this is looking at frames and machines. Going to look at a detailed example so that I can explain the correct procedure for analysis. Okay, so this is adapted from an example from the Engineering Mechanics Statics book by Hibbeler, which many of you will be familiar with. So we're asked to analyze and determine the forces acting on between each member of this thing. So is this a frame or a machine? If you're not sure, you can go and look up the definition, but basically if it's holding a load and the load can never move, no matter what magnitude the load is. Yeah, it's not all the members aren't designed to move relative to each other, then it's a frame. However, if the members of the assembly of components is designed to move and to transmit motion as well as movement, to transmit load as well as movement, then typically it would be a machine. Okay, so with this one, if we took off the load here, P, and the load M, that frame is still going to sit there and not go anywhere. Okay, so this would be a frame. Okay, so in analyzing something like this, what's the usual engineering mechanics approach? So far, you should have done introductory rigid body equilibrium and should be used to dealing with just a single body and drawing free body diagrams and applying the equations of equilibrium. So that's what we're going to do here. So we're going to, I guess, ignore the fact that it's a frame or a machine to start with and just draw a free body diagram of the whole thing, apply the equations of equilibrium, solve for our unknowns, and yeah. So the first step here was to draw a free body diagram. So let me just get my pointer. Right, so the first step in an engineering mechanics problem is to draw the free body diagram. But now that we have a frame or a machine that's made up of many members, we have a choice to make. We need to decide what do we draw a free body diagram of. And I recommend that usually you would start with drawing a free body diagram of the entire frame or machine, okay, and understand it as just one complete rigid body to start with. So if we did that in this case, we've got our two frame members here, take away the supports and replace them with the unknown reactions that we're wanting to find. Okay, so if we do that, what's the problem we have here? We've got 4 unknowns and 3 equations of equilibrium. So just drawing a free body diagram of the entire frame or machine, if it was a machine problem, on its own is not enough for us to solve for all of our unknowns. So we're going to need to do something else, right? Because we've only got 3 equations of equilibrium in a 2D problem. Two force equations and a third equation as the moment equation. Or depending on the problem, it could be 1 force equation and 2 moment equations, or maybe even 3 moment equations. But whatever the case, there's only 3 independent equations that you can use. So now what? First, let's just use the engineering, or continue to use the engineering mechanics approach and see how far we get. So let's now write some equations of equilibrium. So I'll put them up there for you. So in order to make this a specific problem, let's put some numbers and some dimensions so that we can do the moment equation on our free body diagram. So I'm just going to make up some numbers here that weren't any there to start with. So I'm just going to say the load P is 700 newtons and the applied moment here, or applied couple, is 400 Newton meters, and the dimensions are as shown, and they're in meters. So if we take moments about point A, we could have taken moments about point C. Either would do. So taking moments about point A, we have the force Cy causing an anti-clockwise moment about point A. Its perpendicular distance is 2 plus 2 equals 4. So Cy times 4. And then P acting vertically downwards, its perpendicular distance is 4 minus 1 equals 3, tending to cause a clockwise moment about point A. So therefore negative, and the applied couple is in the anti-clockwise direction, so we can just add that in there. That's all equal to 0. So we can rearrange that, and we can solve for one of our, or the first of our unknowns, Cy. Okay, let's move on to the next equation of equilibrium, looking at forces in the vertical direction equals 0. So Cy minus P plus AY will equal to 0. Rearrange that, and we can solve for AY. So we've got two of our unknowns. Now, if we do sum of the forces in the x direction equals 0, we find that we have AX minus CX. Nothing else appears in the equation, so we can't solve for either of those two unknowns yet. All right. So yeah, the best we can say is that AX is equal to CX. So the next thing is, now what? All right, so what's the usual engineering mechanics approach? Draw a free body diagram, apply equations of equilibrium, solve for unknowns. Okay, so let's draw another free body diagram. And this time we're going to draw free body diagrams of the individual parts, and imagine that we've separated them. Okay, so if you look at me across to the side, you can see I've got the frame here, and I'm going to imagine that we've separated these two things. I should really have another one. Right, so we pull them now apart. I originally had a pin in there, or a bolt holding those together. I've now taken them apart, and now I need to put on my free body diagram the forces that are exerted on each of the members. Okay, so what should we draw at the connecting point? Well, if we think about it as just a single rigid body problem, we've got a pin connection here, so we should put on two component forces like this. Okay, we don't have to make them horizontal and vertical. We can make them any orientation we like, but usually the most convenient is horizontal and vertical. So let's put that on. All right, so pin connection. Pin connection, free to rotate, so no moment reaction, but I can't translate one relative to the other, right? I can't move this one over here off to this way horizontally, and I also can't push it up as a rigid body translating upwards, right? I can only rotate. Okay, so let's add those to the right-hand part. So I've now got my unknown reaction forces due to the pin at point B here. Now, what do we draw on the left-hand side here? Okay, we must obey Newton's third law and show over here equal and opposite to what we've shown on the right-hand side. Okay, so with our things connected, what the right-hand side does to the left-hand side does equal and opposite to the right-hand side. Okay, so in here and in this connection, we've got action-reaction pairs of forces. Okay, All right, so let's now that we've got our free body diagram, right, using this right-hand side, let's use our equations of equilibrium. So I've just put here what we calculated previously or determined previously on the previous pages. So let's analyze this right-hand side now. So we've now got Cy and we don't have Cx yet. But now if you look at it, we've got 1, 2, 3 unknowns. So Cx, By, and Bx are our 3 unknowns on this rigid body. P we know, that's our applied load. C we know because we worked it out from the equilibrium and rigid body equilibrium of the whole frame. 3 equations, 3 unknowns we should be able to solve. So let's take moments about point B. Why take moments about point B? Because we've got 2 unknowns here, and they'll drop out of the equation because they both pass through that point, and we'll be able to calculate Cx directly. Okay, so if we put that in, Cy is tending to rotate anti-clockwise about point B. Its perpendicular distance to point B is 2. Right, so there's that. P, perpendicular distance to point B is 1, tending to rotate clockwise around point B. Okay, so pushing down here, tending to rotate clockwise. So that's negative. And Cx, pushing down here, also tending to rotate clockwise. So that one's negative, and its perpendicular distance is 4. All right, so now that we have our equation, all equal to 0, substitute Cy that we found up here, and we can solve for Cx. Okay. And if all we were asked to do in the problem was to find the reactions at the supports, then we could also then apply this equation, Ax equals Cx, and we could say that Ax is also equal to 37.5. Right, so often textbook problems will ask you to do that. In reality, in practice, you're going to want to know the forces at every connection, because if you're designing this thing and at this connection here, you want to transmit that load, you're going to need to know what size bolt or pin to put in there. Okay, so you need to know what the force is here. All right, so we're going to continue on with this analysis. So let's look at some of the forces in the vertical direction and calculate By. So some of the forces acting up in the vertical direction, upwards is positive. So Cy minus P plus By equals 0. So we can solve for By. Okay, some of the forces in the x direction, we have Bx equals Cx. So we get Bx equals 37.5. And then I just repeated that there. So now let's go and look at the left-hand side. So some of the moments about point B for the same reason as before. So we're just assuming or pretending that we haven't worked out what these values are. And we're just going to use the left-hand side and see that we get the same answer. All right, so taking moments about point B, we have Ax times its perpendicular distance, which is 4. Ax tends to cause an anti-clockwise moment about point B, so that's positive. The applied couple is anti-clockwise, so that's positive. And Ay, pushing up here, tending to rotate clockwise, so that one will be negative. No other moments on that body, so it will equal to 0. Rearrange and we can solve for our unknown Ax, which as we expect and hope, it's the same as we found previously by looking at the right-hand side, so calculating Cx and then using our original free body diagram. Okay. So summing the forces in the vertical direction equals 0. On the left-hand side, we have Ay minus By, just the two forces there. So by is 275. Okay, using our AY that we calculated from the original free body diagram of the entire frame. And that also coincides with what we calculated for the right-hand side. Now, I'm not sure if I've written this somewhere coming up, I can't remember. For point B here, when I drew the forces and their senses, I got the sense correct. Right? So my answers came out positive. As I recommended previously, if you get a negative number here, do not go and change your free body diagram. Okay, just continue on, and then write your equations of equilibrium according to what's shown on the free body diagram, and then substitute in the negative values. Okay. All right, sum of forces in the x direction equals 0. So we've just got AX and BX, and we get BX equals 37.5, the same as we got before. Okay. All right. What you should not do when analyzing connected parts. So what you should not do is what I've shown up here. Okay. Do not do that, right? Because this is not all that exists here, right? You're not telling the whole story if you put forces like this on your free body diagram, okay? Because you have equal and opposite forces acting there, right? So don't do that. Okay, so I've basically just said that. So both, right, the forces on both sides exist together, okay? Because right, what's actually happening in here is, you know, we in most solutions that you'll see, people don't write or don't show the pin that's connecting those things together. Okay? So what we have, if we draw a free body diagram of the pin between these two frame members, right, we have on one side of the pin BX and BY from member AB, and then on the other side we have BX and BY from the frame on the right hand side, from frame BC. Okay, so these two here are equal and opposite to these two here, and these two here are equal and opposite to these two here. Right. Okay, further considerations. Right, so I've now just shown the effect of the pin on each of the members. So yeah, I think I've just yeah, spelled out what I just said on the previous page. Okay, and you know, or as the loads pass through the frame member. Okay, so if we separate these things, right, here's one member, there's force, right, B, go this way, let's start here. Actually, let's start A and B, so that's member AB. We've got BX and BY on here, and then those loads are exerted by the pin. So equal and opposite to that, we have BX and BY. And then on the pin, we also have BX and BY that's exerted by the other part of the frame. And then the pin exerts BX and BY onto the frame. Okay, so we need to obey Newton's third law all the way through, from one member through to the next. All right, now let's consider further considerations. Right, so let's consider now the connection at A. So at A, we have again another pin connection. Okay, we have this clevis here. If we separate that, we've got AY and AX. Now this is usually a double shear connection. So we've got these lugs on either side. So this load AY and AX is shared between the two sides, or either side of the frame member on the pin. Okay, so assume that they're distributed equally, so half on each side. So that's the free body diagram of the pin. And these forces here are the forces that this lug, or this side of the clevis, exerts on the pin. Then we can go even further, right? What's the effect of the pin on this lug part of the clevis? Right? So equal and opposite to what this lug exerts on the pin exerts on the lug. And we have the horizontal one as well. And then the ground, or in fact, not really the ground, this base plate, right? We haven't really even got to the ground yet. So, but we can consider it for now as the ground. So we have forces equal and opposite to these, but we're still not in equilibrium because these two horizontal forces here, AX over 2 and AX over 2, separated by a distance, right? So they form a couple. So we actually get a moment generated at the base of this clevis. Okay. So you can imagine that this lug here is welded to the top of this base plate. Okay. So there's a moment load in this weld. Okay. So if you don't include this, right, and if you're doing analysis of the welded connection here, you need to include this moment load. Right? Yeah, so then we could draw, if we take this a step further even, and draw a free body diagram of the base plate, and that's held down by these bolts. Right? In order to determine the size of these bolts, we would need to include this little, or this may not be little, but include this moment effect in the loading for determining the sizes of the bolts. Right? But in most of our introductory mechanics problems, we my pen, right? We kind of just look at that bit of it. Right? And that's why we end up with just reactions like this, and we never actually see the moment that's generated at the bottom of the lug of this pin connection, and also in the base plate, and then through the bolts into the ground. Okay, so that's just further consideration, and to point out that there's more to engineering mechanics and structural analysis than the simple textbook problems would initially lead you to think. Okay, and I've just written that down the bottom right hand corner there. Back to right, and I think that might be the end of the further considerations. Okay, so that's it for this video. Hopefully that was interesting and enlightening and helped you to think a little bit beyond just doing the textbook problems and thinking about the more real practical application of what we're doing, and not being just satisfied with being able to do the textbook problems, but looking beyond them and trying to see the practicality that they're trying to represent. Anyway, that's it for now. See you next time. Bye.